Okay, so let's understand about dynamic programming. Okay, so what is dynamic programming? So dynamic programming is a programming is a programming which basically solves a problem by breaking it into smaller sub problems. Okay, so and this dynamic programming is basically uh, it applies to optimization problems only. So optimization problems in the sense like whenever we try to find the maximum of something, minimum of something. So basically it applies to optimization problems. Okay, next it basically makes choices like make optimal choices from previously made decisions. So whatever decision we have taken earlier, based on that we take the next step or next decision. So it basically makes optimal choices from previously made decisions. Okay, now whenever we are making decision, whenever we are making choice, right? So each choice makes sub problems like original problem. So you can say each choice makes a sub problem like the original problem. I mean, and whenever we are making sub problems, if they are overlapping or if they are common, right? So then basically we store it or store it in a table or we memorize it, right? So in that case, so basically the key is to save or memorize or store these sub problems to save computation time, so that we don't have to recompute the sub problem again, right? To store the sub problem to save the computation time. Now before going into dynamic programming, we should understand recursion very well. Okay, I would highly recommend that you should understand recursion, otherwise you will face difficulty understanding dynamic programming, because most of the problems what we do, like we first try to solve the problems in using recursion, then we try to optimize with dynamic programming. Okay, now that there are generally two types of dynamic programming. One is top down, another is bottom up. So basically top down and bottom up. Okay, so top down is basically when we are using recursion with memoization, and bottom up is when you use tabulation. So basically we store the results in a table. Okay, a recursion is basically either we can use hash map, we can use LRU cache like in Python, then I mean, we can use many things to store, but it is basically still uses recursion. So it has the auxiliary stack space, and then to remove the auxiliary stack space, we generally move forward with tabulation. Okay, so tabulation is basically to make the table storing the results, and whenever we are moving to next step, right? So we refer the step, we refer the result from the previous step. Okay. Okay, so I mean, and top down is basically so top down is when like we have a very large problem and then we are breaking into smaller problem. Okay, so breaking into some smaller problem, so large problem to smaller problems whenever we are going. So basically that is top down. Okay, so we are going top to bottom. Okay, and bottom up is like we have solved a particular step, let's say particular cell, like this particular cell we have solved it for a particular very small problems, and then we are going for the larger problem to solve the larger problem. Okay, so this is the difference between the two, so top down and bottom up. Okay. Okay, so even like if you can remember, like top to top down means when larger to smaller, and bottom up means smaller to larger. I mean, we'll not forget like what is top down and what is bottom up. Okay. Okay, so this is very theoretical, but to understand dynamic programming, I mean, we should take an example. To understand dynamic programming, let's take a very classic example, nth Fibonacci number. Nth Fibonacci number. Okay, so for to get the nth Fibonacci number, the recursion we can write as f of n. Base case we can write as if n less than or equal to 1, return n. Okay, and then return else, return f of n minus 1, f of n minus 2. Okay, so this we can return. Okay, so now I mean, what will be the time complexity? So time complexity will be exponential 2 to the power n. Space complexity would be O of n. Okay, now this O of n is basically for auxiliary recursion call stacks or auxiliary stack space. Okay, pardon if I have done a mistake in spelling. Okay, over here, so now let's try to draw the recursion tree to understand. Okay, so let's say we want to solve for f of 5. Okay, so f of 5, it will require the result of f of 4 and f of 3. Now f of 4 will require the result of f of 3 and f of 2. F of 3 will require the result of f of 2, f of 1. Okay, f of 3 will require the result of f of 2, f of 1. F of 2 will require the result of f of 1, f of 0. Right, f of 2 will require again f of 1, f of 0. Okay, f of 2 will require the result of f of 1, f of 0. Okay, so and over here f of 1 will return what? If it is less than or equal to 1, so it will basically return 1. So this will return 1. F of 0 will return 1. F of return will return 0. So this will return 0. F of 2 will return 1 plus 0, which is 1. Okay, f of 1 will return 1. So f of 3 will return what? F of 3 will return 2. F of 2 we already calculated over here, so f of 2 it will return 1. Okay, so on the left we got 2 plus 1, f of 4 will return 3. Okay, now f of 2 will return, we already got over here 1, f of 1 will return 1. Okay, so 1 plus 1 will return 2. So 3 plus 2 is basically 5. So nth Fibonacci, fifth Fibonacci number is 5 only. But you can see over here, so this is the larger problem we tried to solve. Then we tried to went into solve the smaller problems. Okay, Then but whenever, and this is the base case, like f of 0, f of 1, f of 1, f of 0. So these are the base cases, because we said like if n less than equal to 1, then return n, whatever the number, or if it is 1 or 0, so we just return it. Okay, so we can see like over here, f of 3 we are calculating over here, I mean no need actually. F of 2 we are calculating over here, we are calculating over here. Okay, f of 1, I mean how many times we have calculated, I mean it's numerous time we have calculated f of 1. F of 0 we also calculated over here, f of 0 we calculated over here, f of 1 is over here also, I mean it's too much, right? So in this case we can see like there are overlapping subproblems, right? So every problem, every smaller problems, we are trying to solve it again and again. Can we not optimize it? So whenever we try to optimize whenever we try to optimize the overlapping subproblems, then dynamic programming comes into picture. Okay, so dynamic programming will say like I will take care of it. Okay, so okay, so dynamic programming, so basically what we can say like over here, whatever the results are returning, so we can in the first approach, like whatever the approach we have taken, I mean I lost that last note. So whatever approach we take, so basically we can first take top down. So basically these overlapping subproblems whatever we have, so basically we can memoize these values. So to memoize it, we can refer a DP table of size n plus 1. Okay, and initialize with -1. Okay, then what we will do, like okay, in the case of f of n we are passing, so we'll pass this DP as well. Okay, so let's write over here f of n and pass, will pass DP. Okay, so now we'll copy the base case. If n less than is equal to 1, return n. Okay, now if dp of n not is equal to 1, not equal to -1, return dp of n. So over here what we are doing, so I have written over here, but what we are doing, so basically you are saying like whenever, let's say we already pre-computed result of f of 2, right? So whenever we encounter f of 2, then we can simply return whatever we earlier stored the result. So dp of 2 not equal to -1, then return dp of 2. So it will return what it will return. So 2 will return 2 only. So 2 will return 1 only, right? So in this case, we are referring a memoized value, right? Now we need to store it as well. So in that case, what we can say? We can say return, before returning, we can store the result as well. So dp of n is equal to f of n minus 1 plus f of n minus 2. Okay. So I mean this part we like this part. Now what will be the time complexity? So time complexity would be O of n. Okay, space complexity would be O of n for the DP table and O of n for the auxiliary stack space. Because over here we can reach up to how many levels? 5 level. 1, 2, 3, 4, 5. So this is 5th level, right? So 5th level, we went up to 5th level. So that's why you have written over here also in the recursion also written O of n. So same we will be using over here also. Okay. Now can you remove it? So to remove it, we need to take help of tabulation. So tabulation is another dynamic programming approach, and that is we call it as bottom up. Okay. Now to understand this, let's take a table. Okay, so first we'll initialize 0. So this is 0. So 0 means dp. What will be the result of 0? So it will be 0 only. So if we 0th Fibonacci number is 0 only. So this is 0. Okay, then if we get 1, so what will be the result for 1? So this is 1. So this you already know. Now what will be the result of 2? So this is 0 plus 1, 0 plus 1 equal to 1. Okay, now what will be the result of 3? So 1 plus 1 is 2. Okay, what will be the result of 4? So 2 plus 1 is 3. What will be the result of 5? 3 plus 2 is 5 only. So you can see, like, whenever we are going from next step, so let's say we already know 0 and 1, so that's why we initialize 0 and 1 over here. But whenever we are going to 1, like whenever we are going to position 2, like 0 second, whenever we're trying to find second Fibonacci number, then we are referring the results from the previous two results, right? So previous two results, right? So basically, as we discussed before, so we refer the results from previously computed results, right? Similarly for 3 also, 4 also, 5 also, right? So we can say, we can like, as we have taken a table over here, so what will be the size of the table? So it will be just, if it is nth Fibonacci number, the size of the table will be n plus 1, because you need to find the nth Fibonacci number. Okay, not n minus 1 Fibonacci number, right? Okay, so now with initialize dp of n plus 1, we initialize with 0. Okay, so now what the problem will look like? So f of n, we initialized with n, we have taken a dp of n plus 1, dp table of dp 1d dp array of n plus 1. Okay, or dynamic programming array of n plus 1. dp means dynamic programming. Okay, anyways, now initialize with 0, we have initialized with 0. Now so this 0, everyone is initialized with 0 0 0 0 0. Okay, so everyone is initialized. Okay, everyone is given 0. Okay, okay, so now over here, what we can do, like f of dp of 1, we can initialize as 1, because we know the result, because that is the base case also we have written over here. Less than is equal to 1, return n. So basically n, if n is 1, then return 1 only. So this is done. Now we need to calculate the result from this second index, right? So in that case, we can run a loop for n I is equal to 2i less than is equal to n I plus plus. Now over here, so to get the dp of I, what we referred? We referred the result of dp of I minus 1 plus dp of I minus 2. So to get the result of 2, we referred the result of dp of 0 and dp of 1, right? So you can simply return, we can simply store that, right? And then on the next step, what you can do? On the next step, we can simply return dp of n. So this dp of n will have the result of nth Fibonacci number. Okay, now what will be the time complexity? So time complexity would be same, because we are running a loop over here. Okay, although it is running from second index to n, so I mean, you can still say it is O of n only. Okay, just for simplicity. Space complexity would be O of n, because you are using the dp table of size n plus 1. But we have removed, you can see, like, we have removed the auxiliary stack space over here. Okay, all right, but can we improve it? Can we still improve it? Let's check that. Okay, so over here, so this is current. Okay, so if you refer, this is current, so this is previous 1, this is previous 2. So whenever we are solving the result for this per second index, we are referring the result of this previous the first index and 0th index. So we can call it as previous 2 and previous 1. Okay, to solve current we need the result of previous 1 and previous 2. Okay, so now what is previous 2? We have declared previous 2 is 0. So previous 2, so let's write that. So you can write the same function again. Okay, so f of 1, previous 2 we have written as 0. So previous 2, let's assign previous 2 as 0. Previous 1 we have assigned as 1. Right, previous 1 we know the result as 1. Okay, now we have to run a loop. So now we are running loop for I is equal to 2, I less than is equal to n, I plus plus. Okay, now over here to get the result of current. Okay, so current, to get the result of current, what we need to do? We need to get the result of current, we need to get the result of previous 1 and previous 2. Okay, so basically car is equal to previous 1 plus previous 2. Okay, so now we got the car. Now this this previous one will be car. So previous one will be car, so previous one will move over here, and previous 2 would be previous 1. So this will be previous 2. Okay, so now the code becomes previous 2 would be previous 1, and previous 1 would be car. Okay, and where will our result will be stored? So it will be on the previous only, because at the end we are swapping current with previous. Okay, so in that case we can return previous, or sorry, previous 1. Okay, so you can return previous 1 and previous 1 will have the result. Now I think I got a specific case, I forgot to add a specific case over here. So we can simply say if n is equal to 0, you can simply return 0. Then we don't have to do all this drama. Okay. All right, so what will be the time complexity? So time complexity would be O of n, because still we are running a loop over here. Space complexity will be O of 1, because we are using just two variables, which is constant. Okay, now what is the difference between greedy and DP? So greedy and DP is like, greedy is also we apply to optimization problems. Okay, optimization problems. But greedy and DP does not have greedy or divide and conquer does not have overlapping subproblems. So that's the one of the main reason actually. So greedy does not have overlapping subproblems. Okay, so another thing is like, it is just to make the locally optimal choices to reach to faster destination, faster decision actually. So I mean, it is basically faster than DP. Okay, so what you can say, it is basically uh, to make locally optimal choices to reach to a faster decision. Okay, and it is faster than DP. Okay, enough theory now. We'll see in the next video. Okay.